Okay, so we are live. Let me share my screen. So can you confirm that you can see? Anyone can confirm? The screen is visible?
Yes, sir.
Okay, thank you. So in the last class, we looked at classical cryptography, especially a couple of ciphers and its cryptanalysis. And I have given you assignment 1 for that. Now, there is a concept. This was all classical cryptography, So mainly before Shannon, people have developed a lot of work. Shannon actually gave a kind of theoretical foundation to cryptography, So, actually he gave a result regarding perfect secrecy. So, what do you mean by perfect secrecy? That means even if someone has the ciphertext with them, but they can obtain no information about the plain text by observing the ciphertext. So this is something an important thing. So if this happens, then our crypto system is perfectly secure. So I will show you that shift cipher is actually a perfectly secure system. And in fact, so this is something really an important result. And so these ideas, the Shannon ideas, are based on basically probability and certain concepts in information theory like entropy. So first I will describe probability theory, elementary probability theory, and then we will talk about perfect secrecy. Then I'll also give talk about one-time patch system, which is again a crypto system. And you can see that these are perfectly secure. So one-time patch system was very famous at one point of time, and I think after people know that it is perfectly secure. So what are these concepts? Let me talk about it. So basically this is before we start private key crypto system. I'm just building some concept in between. So okay, some theoretical foundation for it. Okay, so let me choose a pen, and now we are ready. So first of all, security of a crypto system we can define in actually 3 parts. So let me say something about it. So the first thing is there are systems which we call them computationally or computational secure. What do you mean by that? So actually there are 3 kind of secure crypto systems. One is computationally secure. What is the meaning of computationally secure? If best algorithm for breaking, it requires large number of operations. It requires, say, at least n operations. Okay, where n is a very large number. So such crypto systems are known as computationally secure. Then there is another concept known as probable secure. This is something like NP complete definitions if you are aware of. Okay, so probable secure means okay, a crypto system is secure if a given integer cannot be factored, for example. Okay, so that kind of systems are probable secure. Third is unconditionally secure. unconditionally secure. Unconditionally secure. So if it cannot be broken, this is the important one, cannot be broken even with infinite computational resources. Certainly it will be very good, unconditionally secure. I think I will show you that certain crypto systems are unconditionally secure later on. So these are the broadly, three kind of security that you can talk about crypto system. Computationally secure. If best algorithm for breaking it requires at least n operations and is a very large number. Probable secure. If it, so if a system is probable secure if a given integer cannot be factored. This is an example I'm giving you. Unconditionally secure if it cannot be broken even with infinite computational resources. Okay. So now I think I'm going to recall some elementary probability theory because I hope you might have done these things, but still, I just want to have it here in our notations. Elementary probability theory. Okay. And the idea that we are going to take first is random variable, especially discrete random variable. Okay. So I am going to talk about discrete random variable. Sometime I write it at DRV, discrete random variable. Okay. So what is discrete random variable? So a discrete random variable, say capital X, okay, consists of two things: a finite, set X, and a probability distribution defined on X. There are two things. It's a discrete random variable X bar, we denote it by X bar, consisting of two things: a finite set X and a probability distribution defined on X. Okay, then it is a random variable, discrete random variable. So we denote, there are certain notations. The probability that the random variable X bar takes on the value X is a member of capital X, okay, is denoted by PR bar is equal to X. This is the notation. Or if X bar is clear, if X bar is fixed, so we simply denote it by PR X. Okay. So the probability that the random variable X bar takes on the value X of the set X is denoted by this. Okay. Now, of course, there are certain, this probability of X is non-negative number for every X in X, and this probability sum should be 1. Of course, this is the condition that should be true, right? So this is the basic definition of discrete random variable. So what is a discrete random variable? Again, I am recalling a discrete random variable consisting of a finite set X and a probability distribution defined on X. Okay. So this is a discrete random variable. Okay. Now, as an example, I can give you an example of discrete random variable here. Okay. Suppose X is a set consisting of heads and tails. Okay, and we define the probability on this. Probability of heads is same thing as probability of tails is half. So this is the probability distribution, right? This is a probability distribution defined on this set X. So together these two things. So basically I can say that coin tossing is a discrete random variable. Discrete random variable, right? As an example. Now I can give you an idea of event. What is event? Suppose X bar is a discrete random variable DRV defined on X, and E is a subset of X. Okay, subset of X. So the probability that X bar takes on a value in the subset E is nothing but probability X belongs to E. Okay, same thing as probability of X, we can call it as X belongs to E. So in this case E is called as a event. Okay, E is called as a event. So we talked about discrete random variable, and if X bar is a discrete random variable, then if E is a subset of X and we have a probability distribution there, then that is a event. Again, I can give you an example. Okay, so random throw of a pair of dice, if you are throwing them, this can be modeled as a random variable Z bar defined on the set, Z is equal to 1, 2, 3, 4, 5, 6, because there are 6 possibilities in one dice. Cross product 1, 2, 3, 4, 5, 6, right? Right. So random throw of a pair of dice can be modeled as a random variable Z bar, like this. Now we can compute the probability distribution, right? So of course we can say that. So of course we need to give the probability distribution also. The probability of I comma j pair is 1 out of 36, right? Every ij belongs to Z. So remember, a discrete random variable consisting of a set Z and the probability distribution. Okay, so this is given to us. Now I can consider the sum of two dice. Consider the sum of the two dice. Now each possible sum defines an event, right? Because this is a subset, okay, of Z, right? So what we can do, we can compute the probabilities. Suppose we want to compute the probability. Suppose Suppose you want to compute the probability that the sum is 4. Sum of the two dice faces 4, right? So this corresponds to an event. I can write it as S4 is an event consisting of 1, 3. This is one pair, 2, 2, another pair, 3, 1, another pair. And this is a subset of Z, right? So now I can compute the probability that's of S4 is 3 out of 36, which is easy to compute, right? Which is nothing but 1 by 12. So we can actually compute different probabilities. So actually, if I define Sj as the event that the sum is j, it is easy to compute the probabilities for each of them. I can just write it down actually. So I can compute that probability of S2 is same thing as probability of sum is 2, sum is 12, same thing as 1 by 36. Okay, probability of S4 and probability of S10, that sum is 10, is same thing as 1 by 12. Probability of S3, same thing as probability of S11, you can compute, is 1 by 18. Probability of S5 is equal to probability of S9 is equal to 1 by 9. Probability of S6 is equal to probability of S8, 5 by 36. Probability of S7 is 1 by 6. So it's easy to compute all these probabilities that when the sum is 2, 12, 4, 10, and so on. Okay. For each of the event, we can compute the probability. Now there is another important, definition: joint probability and conditional probability. So we can talk about joint probability and conditional probability, and then of course, what is the relationship? So we can talk about joint probability. Okay. Suppose X bar and Y bar are discrete random variable. So that means there is a set X and a probability distribution. There is set Y and the probability distribution defined on Y, right? That is given to us on sets X and Y. These are discrete random variable. Then the joint probability X comma Y, this is the joint probability. The probability that X takes on the value X and Y takes on the value Y, right? The joint probability. Then we also have conditional probability. Conditional probability. What is conditional probability? We denote it by PRX pipe Y. So the probability that X takes on the value X given that this is very important, given that Y bar takes on the value Y. This is the conditional probability. Okay, and so these two random variables X bar and Y bar are said to be independent random variables. I call it IRV, independent random variables. Independent random variables if we have probability of x comma y, conditional probability x comma y is same thing as probability of x, probability of y, product of these two for all x in x and y in y. Okay, so this is known as for independent random variables, this is the case. Okay, so note that so we in fact I am moving towards Bayes theorem, which is a very important theorem. Some of you might be remembering it. So okay, note that PR x comma y is same thing as PR x condition y and PR y. Interchanging x and y will give us PR of x comma y, joint probability, same thing as conditional probability yx, this. Using these two, we can simplify to get what is known as Bayes theorem. This is quite useful in computing the probabilities of different events. So let me put it like this. If PRY is positive, then PR of x condition y is same thing as PR of x, PR of y condition x divided by PR of y. Okay. So one corollary. So this, as you can see, that by using these two, we can compute this, right? Because I can just take care of these two are equal. So from this, we'll get this. Okay, corollary is this. If x bar and y bar are independent random variable IRV, so if and only if PR of x, y, x condition y is same thing as PR of x. This is from the previous result, right? For every x in x and y in y. Okay, so this is the Bayes theorem. I can quickly talk about an example here again so that you know what is going on here. Another example here. Okay. Suppose we consider random throw of a pair of dice. Suppose x bar is the random variable defined on the set x to 12, sorry, 2, 3, 4 and so on up to 12, obtained by considering the sum of two dices. These are the all possibilities, right? Now, suppose y is a random variable which takes on value on the value d if two dice are same and value n otherwise if they are not same. right? Then we can compute probability of D as 1 by 6, probability of N as 5 by 6. I can compute conditional probability D 4 as 1 by 3, probability of 4 D as 1 by 6, etc. I think these are easy things. This is all for basic probability theory that I wanted to cover. So conditional probability, so you should know, again I'm just recalling, discrete random variable. Discrete random variable, so x bar is a discrete random variable consisting of a finite set x and a probability distribution defined on x, right? And then we can define the probability that random variable x bar takes on the value x as this quantity, right? If x bar is fixed, we denote it by PR of x, and that's what we are using all the time notation. Then we have talked about event. When x is a subset, when e is a subset of x, then we can define event, right? Then I gave you an example. Joint probability I talked about, probability that x takes on the value x and y takes on the value y. Conditional probability, the probability that x bar takes on the value x, given that y bar takes on the value y, right? Then we talked about independent random variables. Bayes theorem. This is very important, that probability of x condition y is same thing as probability of x times probability of y condition x divided by probability of y, if probability of y is positive, right? And x and y are independent random variables if and only probability of x condition y is same thing as probability of x. So I think after this, we are ready to talk about perfect secrecy. This was very brief thing that we require in probability theory. Perfect secrecy. Okay. I'll give you, the definition of perfect secrecy. Then I will talk about a characterization of perfect secrecy, which was given by Shannon. And then we'll talk about, a couple of other things. For example, okay, I'll show you that shift cipher is a perfect secret cipher. So we can talk about a crypto system P, C, consisting of P, C, K, E, or D. You remember? And K belongs to K, is a key used for only one encryption. Okay. So this is a crypto system, and then now you see how we can look at plain text and cipher text, everything, uh, random variables. Okay. So now there is a probability distribution on the plain text P. This implies that plain text elements define a random variable x bar. Okay. A prior probability that plain text x occurs, we denote it by PR x bar is equal to x. Okay. Now assume that key K is chosen using some fixed probability distribution. assume that key k is chosen using some fixed probability distribution. This implies that key also defines a random variable, right? And we denote it by k bar. So plain text, elements define a random variable x bar, key defined a random variable k bar. Okay, so this is good enough. And probability that key k is chosen, we denote it by k bar is equal to k. Just standard things, right? Since k bar is a random variable. Okay. Now we assume that the plain text, that the key and plain text are independent random variables. This is our assumption, right? So that means conditions are there. Now, so we have a probability distribution on the plain text, we have a probability distribution on the key space, right? On the key. So this will induce probability distribution on C, our ciphertext. Okay. So this implies that we can consider the ciphertext element as a random variable. We call it as y bar. Okay. And then the probability, corresponding probability, y bar is equal to y. That y is a ciphertext that is transmitted, right? Now, for a key, small k in capital K, define C of k ek of x such that x belongs to P. Okay. So this is nothing but set of possible ciphertexts if k is the key, right? So this is we can define. So that means for every C, y in the ciphertext C, I can compute this probability y bar y. This will be summation, of course, for probability of k bar as k times probability x bar as dky. And of course, this is over k such that y belongs to ck. Okay. So remember, plain text is a cipher, is a random variable. Key space for a given k, is a random variable, and then we have the ciphertext as a random variable, right? So we can compute the probability. Okay. We can also talk about condition probability. So I think I can write down here. Observe that for any y in C and x in P. So y is a ciphertext, x is a plain text. The conditional probability PR of y bar is equal to y and x bar is equal to x. That means probability that y is a ciphertext given x is a plain text. We can compute it as summation k bar is equal to k such that x is equal to dky, right? Okay, and the conditional probability using Bayes theorem, I can compute using Bayes theorem. Probability of x bar is equal to x, y bar is equal to y will be probability of x bar is equal to x summation into probability of k bar is equal to k, where summation is over k such that x is equal to dky. Dky is a decryption rule, right? If you remember, divided by summation probability of k bar is equal to k. This is basically using Bayes theorem. I'm not doing anything new here, just writing you Bayes theorem in terms of these notations. Probability of x bar is equal to dky, and this summation is over k such that y belongs to ck. Okay, so this is these are all probability. I think it will make more sense if I'll show you an example. So that will make more sense. Let us talk about an example. So what we are doing here, I'm computing the conditional probabilities, right? This is using Bayes theorem. Right, the conditional probability I am computing. So let us look at an example. Suppose plain text P is A comma B, right? So, and the probability distribution A is 1 by 4, probability of B is 3 by 4. Suppose K having keys K1, K2, K3, right? With probability of, so this is also a random variable. Probability of K1 is equal to half. Probability of K2 is equal to probability of K3 is equal to 1 by 4. Suppose C is ciphertext 1, 2, 3, 4. Okay. And encryption functions are like ek1 of A is equal to 1, ek1 of B is equal to 2. These are the encryption functions. ek of 2 of A is equal to 2, ek2 of B is equal to 3, ek3 of A is equal to 3, and ek3 of B is equal to 4. So actually all this can be written in the form of an encryption matrix. I am just writing, which will be easy for you to remember. K1, K2, K3. Encryptions are 1, 2, 2, 3, 3, 4. You can see that, right? So these are the encryption functions. You can see the EK1. K1 of A is 1. K1 of B is 2. K2 of A is 2. K2 of B is 3. K3 of A is 3. K3 of B is 4. All encryption functions. All these can be written in the form of this encryption matrix. So what is given to us? Okay. Plain text is a random variable. So plain text is given. The probability distribution is given. Key space is a random variable. So again, this is given as a probability distributions are given, and the encryption rule is given, and the ciphertext is given. So basically, I can compute the probability distribution on C now. How do we compute? So probability of 1, this element I am taking, will be what? Okay. So basically, 1 we are getting from EK1A, right? So K1, what is the probability of A? A is 1 by 4, 1 by 4. Okay, A is 1 by 4 from here, and ek1 k1 key even is 1 by 2 here, this one. So this is 1 by 8. Similarly, I can compute what is probability for 2. 2 will be p by 4. So 2 is what? You see, 2 is here. So ek1b and ek2a is 2, right? So I have to use this and this encryption rules from here, right? So 1 is 3 by 4 into 1 by 2 plus 1 by 4 into 1 by 4, which is nothing but 7 by 16. I hope you got it why we are, how we are getting this. This is for B, okay? And this is for K1. This is for A and this is for, you know, K2, okay? This is how we compute. So similarly, I can compute all other ones. For example, probability of 3 will be 3 by 4 into 1 by 4 plus 1 by 4 into 1 by 4 is equal to 1 by 4. I can simplify, right? Probability of 4 will be 3 by 4 into 1 by 4 is equal to 3 by 16. Right, so this is the probability distribution on C I can compute. Once we compute the probability distribution on the ciphertext, we can also compute the conditional probability, which I can, I can just write it down now for you. Probability of A condition 1 is 1. Probability of B condition 1 is 0. Probability of A condition 2 is 1 by 7. Probability of B condition 2 is 6 by 7. Probability of A condition 3 is 1 by 4. Probability of B condition 3 is 3 by 4. I'm just writing now rather than computing. You can compute it directly. Is 0. And probability of B condition 4 is 1. So these are all conditional probability on the plain text given a certain ciphertext. Okay. So this is all about. Okay, so I think now I am ready to define what is known as perfect secrecy in a formal way. Okay, so I talked about plain text as a random variable, key space as a random variable, and ciphertext as a random variable. So now we can define what is known as perfect secrecy in these terminologies. Perfect secrecy. So a crypto system, I can say that a crypto system has perfect secrecy if condition probability of x given y is same thing as probability of x for all x in the plain text and for all y in the ciphertext. If this happens, then we call it as a perfect secrecy. In other words, we say that a posterior probability that the plain text is x, given that the ciphertext y is observed, is identical to prior probability that the plain text is x. Okay. Loosely, that means Oscar can obtain no information about the plain text by observing the ciphertext. Okay, because these probabilities are same actually, right? So okay, this is something very important now. Now I think I'll give you one theorem. Okay. And I'll show you that shift cipher has a perfect secrecy. Okay. So suppose that the 26 keys in the shift cipher are used with equal probability 1 by 26. Then for any plain text, probability distribution, the shift cipher has perfect secrecy. Okay, so we are assuming that the 26 keys in the shift cipher are used with equal probability 1 by 26. Okay, all 26 keys are used with equal probability. Then for any plain text probability distribution, the shift cipher has perfect secrecy. So I think it's a very a small proof. So I would like to give you this small proof here. Okay, and so let me give you a small proof here. So here P is equal to C is equal to K is equal to C Z26, and for 0 less than or equal to K less than or equal to 25, the encryption rule EK of X is equal to X plus K mod 26. X is in Z26, right? Now compute probability distribution on C. Let Y is in Z26. Then probability of Y bar is equal to Y equal to summation K belongs to Z26. I'm just computing the formula which I have written earlier. Probability of X bar is equal to dky, right? And this quantity turns out to be, because probability of choosing each key is 1 by 26, right? So this quantity will be 126. That will come out. Summation K belong to Z26. Probability of X is equal to dky, right? So X equal to dky is nothing but X bar is equal to Y minus K. This is our decryption rule, if you remember, right? Now for fixed Y, the value Y minus K modulo 26 is a permutation of Z26, right? So this quantity here is same thing as summation X belongs to Z26, probability that X bar is equal to X, and this quantity is 1 anyway. So this whole overall quantity is 1 by 26 for any Y is Z26, right? So that means the probability of Y or the ciphertext is this, right? Next, we can compute. So remember, for perfect secrecy, I have to show this thing, right? So now let us compute probability of X comma Y, or probability of Y condition X will be probability of K is equal to Y minus X mod 26 is equal to 126. So for every X and Y, there is a unique key. There is a unique key K such that EK of X is equal to Y is K is equal to Y minus X mod 26. So now we can apply Bayes' theorem. So we know this value is 126. So X condition Y will be probability of X, probability of Y condition X divided by probability of Y. This quantity is so probability of X times 1 by 26. This quantity is 1 by 26. These two cancels out and you are left with PR of x. Therefore, we have a perfect secrecy. So shift cipher is unbreakable provided that a new random key is used to encrypt every plaintext cipher. Okay. And exhaustive key search will not be succeed in breaking a crypto system that achieves perfect secrecy. So this is something, it's important one. So shift cipher is perfectly secure. Okay. So I think I can maybe show you that shift cipher, or it is okay. I mean, yeah. So basically, exhaustive key search will not succeed in breaking a crypto system that achieves perfect secrecy. So that is something you can try. So basically, you can try different key. For example, if y is equal to 10, so k is equal to 0 will give you x equal to 10, k is equal to 1 will give you x equal to 9, k is equal to 2 will give you x equal to 8, and so on, right? So as we consider all 26 possible keys, we get corresponding 26 plain text. So no plain text can be ruled out. So basically, you don't have a exact mechanism to find the plain text. So that means EKS will not succeed in breaking a crypto system that achieves perfect secrecy. I think that's all for today. So we talked about perfect secrecy. I showed to you that the shift cipher is a perfectly secure system. Okay, because PRX condition Y is same thing as PRX that I have shown to you. And we talked about build a background for probability and the certain results about the perfect secrecy. So I think that's all. I will talk about one characterization of perfect secrecy in my next class, and then we'll talk about the entropy, and that will finish this chapter also the second chapter. Okay, so that's all for today. So if you have any questions, just let me know. We can close. I think you are enjoying the assignment. We'll be giving another assignment soon to you for this one as well. Okay. Okay, so let me close it.